Now again, LMTD for the counterflow, if we have a counterflow heat exchanger where the direction of the flow of the hot liquid and the cold liquid, they are opposite. So in this case, the hot liquid is going that way and the cold liquid is going that way. Again, we can find the temperature difference 1. Temperature difference 1 is the temperature of the hot body at the inlet minus temperature of the cold body at the outlet. Because this is my side 1, so delta T1 is going to be on this side. So I got the temperature of the hot at the inlet and temperature of the cold at the outlet, because this is the outlet of the cold. Now on this side delta T2, temperature of the hot at the outlet, temperature of the cold at the inlet. That will give me delta T2. Now the curve is going to look like that. So this is your first, this is number 1, this is number 2 side. So the delta T1 is that one, which is the hot inlet, cold, that should be cold outlet. Yep. That this one, there is an error here. This should be a cold outlet. That should be CO, cold outlet, yeah, because it's a delta T1. On the other side, okay, here, before I start, temperature, let's say here was 100 degree, it's a hot. When it comes here, it might be like 70 degree, yeah, because it's going to cool down. Temperature of the cold here is, let's say, is 10 degree. When it comes out on this side, maybe it's 30 degree, rather 30, let's put 20 degree, yeah, depending on the flow rate. So you can see the temperature between 100 and 10. If I do 100 minus 10, that's 90. But if I do 100 minus 20, that's less difference. Hence, you see here, the difference of delta T1 in this case is usually less for the non-counter flow, for the parallel flow. Parallel flow, the difference will be a lot more as compared to this difference. Delta T1 will be bigger for the same temperatures. Okay, so we got all these equations. Now the equation for the LMTD, it's UA delta T2 minus delta T1 divided by ln delta T2 minus delta T1. Okay, going to the next one. So we don't need to actually rework the equations derivation. Now, if we have a look at the LMTD for the different values, now if I CH and CC, the hot and the cold, if we got for condensing, if we are doing like a condensation where the CH goes to infinity, which is that line, CH is always going to be greater than CC. This axis is a temperature, this axis is the length of the heat exchanger, the size of the heat exchanger tube. Now in evaporation, CH is always lower than the CC, yeah, where C can go all the way to infinity. Infinity line is always straight. If they both are equal, like we're using the same fluid, what does it mean? We are using the same fluid here. You putting the water in and hot water in, and the jacket is also a cold water which absorbs the heat. The amount of the heat absorbed by the hot should be same as the amount of the heat lost by the other one. And the line are going to be, the absorption rate will be linear, like two lines like that. Because the coefficient of the heat absorption of the hot fluid and the cold fluid, they are exactly same.
Hence, it's known as log mean temperature difference. So,
okay. Now, in case if you are putting, let's say, iron, molten iron, obviously we can't put that in a radiator, but just imagine molten iron one way. Iron has a coefficient of heat coefficient is very low. The water, if I just give you a rough idea, it's around 300. For the water, it's around 4,200. So massive. The water can absorb a lot of heat per kilogram, and to change the temperature of water by 1 degree centigrade. But iron just need 200 or 300 kilojoules of the heat, joules of the heat, to raise the temperature by 1 degree. So iron, the value of the specific heat is very low as compared to that one. So in that case, what will actually happen is you will look at that graph, yeah, because this is, imagine, specific heat of the molten iron, and this is specific heat of the water, yeah. So that's how the graph is going to look like. If these hot body has hot fluid has a high specific capacity, the graph is going to look like that. Let's move to the next one. This is exactly the same thing, but in a bit more explanation. So if you want to have a look at that one. Now, then we got the same derivation here. This is exactly the same derivation. This is delta D. I put D phi, so we can use the same formula. So it's exactly the same derivation, but a bit more explained. If you want to find out the change in the temperature, you can use this formula here as well. That is another equation. So you can use that one if you want to find the change, the mean temperature difference, where Tm is the mean temperature difference. So this is the mean temperature difference. We can use that formula. Now, this equation here is known as LMTD, log mean temperature difference. If we use the counterflow, we will get the similar answer. So the counterflow, no, that's a parallel flow. The parallel flow, the fluid is going, the cold fluid is going that way, the hot fluid is going that way. The temperature of the cold fluid will increase at this side. Temperature of the hot fluid will decrease at that side. Yeah, okay. Now here the A is the surface area. This should be an A as well. It's the surface area of the tube. That's the surface area of the tube. U is the coefficient, and the others are just change in temperature. Okay. In counterflow, this is how the graph look like. The temperature difference at the inlets is low as compared to the temperature difference in the parallel flow, because that's very cold and that's very hot. But in this case, this is very hot and this is a little bit hot because it's moving in this direction. So the temperature difference is low. Yep. As you move on the other side, at the outlet side, the temperature of the hot fluid and temperature of the cold fluid, the change in temperature will be more than the here. If you have a look at the other one, it's kind of opposite. Yep. Okay. Formula is going to be same. Now there's a cross flow. The cross flow is when, let's say, the hot fluid is going this direction and the cold fluid is flowing in this direction. So that's a cross flow. Both the flows, they are at right angle to each other. We use that one in industrial boiler where the hot gases flow in a path normal to the water and stream. So normal mean 90 degree. So they make an angle of 90 degree, the hot and the cold. The tubes, they are all often finned to improve the efficiency. Now, if there are some deposits, sooty deposits on the outside, if they are left, they will actually minimize the efficiency. Large steam condensers are actually used in this type, cross flow type. Okay, let's have a look at the work example.
This is a log. This is.
Let's have a look at one of the work examples. Now we got an exhaust pipe is 75 millimeter in diameter. So diameter of the exhaust pipe is provided. And it is cooled by surrounding it with a water jacket. So there's a water jacket. So it's mean the other fluid that's flowing is water. The exhaust gas enters. So the temperature that enters is 350 for the hot fluid, which is the gas. And the waters, which is a cold fluid, enters at 10 degrees centigrade. And we are trying to do in the parallel flow. So we assume they're entering from the same side for the parallel flow. The surface heat transfer coefficient for gas and water are 300 and 1500. Now the surface heat coefficient are given by this value Hg and Hw. The Hg is 300. I want to convert into kilowatts because everything we will do in like kilos. So 0.3. And the other value I can convert that into 1.5 for the water. The wall is thin, so it's a thin wall, so there is no temperature drop because of conduction. The gases has a specific heat capacity, so I call Cp for the gas, I call Cpg. Cpg is 1130. It's given specific capacity, and that's joules per kilogram Kelvin, so per kilogram Kelvin. And then the other one is Cp water, Cpw. The Cpw is 4190. 4190. If it's not given, always take as 4200. But if it's given, just follow the sign, follow the value. Sometimes it's 4180, sometimes it's 4200. The flow rate of gas, gas flow rate, m dot for the gas is, this is kilogram per hour, is 200. Yeah, kilogram per hour. I'm not putting the units, but units are here. And the m dot for the water, it's 1400 kilograms per hour. Find the length of the pipe. So we need to find the length of the pipe. To find the length of the pipe, the first thing we need to do is we need to find out the value of the U coefficient, overall coefficient. So 1 over U is equal to 1 over the coefficient for the gas plus 1 over the coefficient for the water plus the heat, the coefficient because of the conduction, yeah, which is x over k, where x is the thickness of the cylinder and k is the constant. Now in the question it says it's a thin wall. If it's a thin wall, this thing will become a 0 because it is a thin wall. Now I put the value 1 over U equals to value for that one is how much? 0.3. And the value for this one is 1.5. If I put that in the calculator, I will get an answer 4. So 1 over U is 4, which means U is going to be 0.25. Okay, everyone, the next thing we need to do is we need to find out the heat lost by the gas. To find the heat lost by the gas, I got the Qg equals to the mass flow of the gas, which is mg, and Cpg, and the temperature drop of the gas. When the gas enters, it enters at 350. When the gas left, it was at 100. If you want, you can convert in Kelvin, but they will give you the exactly same answer. So you will have 250 as a change in temperature. Mass flow rate for the gas was 200 kilogram per hour. The Cp for the gas was 1130. Let's put the values in. When I put that in the calculator, I got the value 56.5 times 10 to the 6. So that's time to 10 to the 6. And the units are joules. The units are joules per hour because the mass flow rate was in hours. Okay, then I am running out of time, so we make another video now.